Hello, everybody. Welcome to Chapter 3. In Chapter 3, we're going to study linear maps. And some books also call this like linear transformations. It's not exactly the same as the linear function I have seen in probably a college algebra class, or not the case. There's some similarity, but not exactly. And for the linear maps, we are going to define this in the section 3.1, and then we're going to talk about if we put the linear maps all together, or from a vector space V to another vector space, say W, or then that's give us a vector, actually another vector space containing all those linear maps. And then once we know this, we're going to move on to look at maybe what is the null space, what is the range of a linear map, and then we're also going to talk about the other things, because if we have a vector space, then you can also talk about the basis or the other things. Or if the linear map is from the finite dimensional vector space to another finite dimensional vector space, or we would like to see if there are another way to represent that, or for instance, by a matrix, which we are more familiar with matrices from a linear algebra class, right? So there are many other things we're going to talk about in this chapter 3. All right. So the reason we studied the linear maps is because if we only have a single vector space, I mean, it's still an interesting topic, right? So to look at what is the structure of that vector space, how many maybe subspaces we can have, or can we write that or decompose that into like the direct sum of subspaces? There's still a lot of interesting questions, but think about like the functions, right? So the functions usually, when we say earlier, is defined maybe from like the a real number set to a real number set. So functions can help us to actually apply those concepts to solve the real life problems. All right, because that make a connection between two sets. And then that's the same idea for the linear maps is, well, if we want to study the relationship between the two sets or more sets, or two vector spaces or more vector spaces, then we need some kind of more advanced tools or new tools, right? So the linear map is something we look at in this chapter 3. And in the real world, of course, some phenomena are more complicated. They're not linear, but a lot of times we could use reduce that to a linear problem, or we can use a linear problem to approximate a more complex, nonlinear problem. All right, so that's why we have a thorough understanding on the linear map. It's very important to understand the even higher level mathematical materials in many fields. All right, so let me go ahead and share the Word document here. All right, so chapter 3, linear map. So we're going to probably break down the material in the section 3a, the vector space of linear maps, into 2 recordings. In this recording, what I'm thinking is, let's define the linear map, let's look at the properties, let's look at some examples, and then let's prove a proposition. And then in the next recording, maybe let's focus on actually the vector spaces containing the linear maps and their properties. All right, so that's roughly speaking how I think probably naturally we can stop at one point in the middle, or have 2 recordings to cover this section. All right, so let's begin with the definition, as we have done in many other sections. We begin with definition saying a linear map, or sometimes also called a linear transformation, from a vector space V. Or we do not always spell out this vector space, but every time we mean this is a vector space when we say a capital letter here, or to another vector space W. This is a function T, taken elements in V, or the vectors in V, and then map them into another vector space W, and with the following 2 properties. Okay. So the first one is additivity. This one basically saying, if you add the 2 vectors in the vector space V together, right, and then you apply this map T over this sum, then of course, then you're going to map that sum of u plus v into another vector in the vector space W. But this is the same as you can apply the t on each vector separately. You have the t evaluated on u first, and then t of v, and then add this up. Right? So this is the first property in order to make a map to be a linear map. That's the first thing required. The second thing is called homogeneity, or homogeneity, or I'm not sure if I pronounce that correctly. Right. But this one is saying is we have a t of a scalar a times v. I remember the any vector space is closed under addition and the scalar multiplication, right? So if you have a scalar times v, it's still a vector in the vector space v here. If you apply the t, you get something in the w space. But this is the same as a, right, times t of v here, all right, t of v here. So then this is, of course, it's a universal statement. So we want this hold for all uv in v and for all the scalar in f, all right, and all v in v. Okay. Now, let's make some examples. Immediately using, we're going to make more examples. But let's make some examples using the very simple ones. The basic functions we have seen for instance, in a linear or college algebra class, right? So, for example, let's consider t from real numbers to real numbers, right, defined by something like a t of any real number x is equal to 5 times x. Right. So if you want to show this is linear, show t is a linear map from R to R, or in this case, the V and the W, they're the same. Right. Then how do we show something is linear? You have to check two things. First is you ask yourself, for any two real numbers, if I apply the t on the x and y, what I'm going to get, right? Well, t of x is 5 times that input x. So x plus y is the input. So t of xy is 5 times x plus y. And you can distribute the 5 is 5x plus 5y. And then obviously 5x is t of x, 5y is t of y. So then that tells you, yes, we have the first property satisfied. All right, additivity. All right, that's okay. And then the second thing is for any, let's say alpha, in this case, let's take the field also to be the real numbers, or from the R, and then any x in R. So do we have the any a in R, right? Do we have t of ax? Well, t of ax is 5 times ax, but for real numbers, we can associate them any way we want. It's a times 5x. Well, 5x is just a t of x, because every x input you multiply by 5, right? So this, therefore, this t is a linear map. Right, a very basic example, but that's kind of help us understand what we need to do when we verify something is linear or nonlinear. And let's make another example here. Maybe let's call this t to be still from R to R, right? Let's say this is defined by maybe t of x is equal to x squared, right? A very basic one. All right, just the square function. Then show this t is not a linear map. All right, sometimes something is not, also is nonlinear. Right? So then we have two properties. Or sometimes given map will satisfy the property 1, sometimes will satisfy the property 2, or only when both properties satisfied is linear. If one of the properties fails, then it's not linear, or sometimes maybe both properties fails, right? So in this case, you just need to argue, which one you pick up one, right? If you believe the first one fails, then how do you argue that it does not true? Well, that is a universal statement. For any x, any y, t of x plus y need to be t of x plus t of y. So if you can take one x, one y to show the t of the sum is different of the sum of the maps, then you're done, right? You prove that. You prove the one property fails. So for instance, we can take x to be 3 and y to be 4, or you can pick up some different numbers. Then let's look at what is the t of x plus y in this particular case. Is t of 3 plus 4 is t of 7, which is 7 squared is 49. However, the t of x plus t of y, well, t of x is 3 squared, t of y, remember we're squaring each input, is 4 squared. So this is 9 plus 16, which is 25. All right. So since t of 3 plus 4 is not equal to t of 3 plus t of 4, right, the t is not linear. All right. So when you show something is a not linear map, you need to show at least one of the properties fails. All right. So that's the idea. Now, what are the other things we want to say here? Let's introduce another notation before we move on to the other more abstract examples here, right? So the set of all linear map, right, from V to W, because if you have two vector spaces, maybe there are many different ways to define the different linear maps over this from the V to the W. All right. So then this is denoted. All right. We're using this notation. We put a capital L. I guess that stands for the linear map, and from the V to W. All right. Is this a collection of all possible linear maps among those two vector spaces? And then this one, keep in mind, is something we're going to treat more carefully in the second recording here. Of course, we have more to say, along the future sessions, right? Right. But right now, let's turn back to the examples, more examples of the linear maps. All right. So we're going to write down some of this. I think it's up to you. Are trying to verify each of this actually indeed is a linear map. All right. So the first one is a very special one, is the 0. All right. So then we're saying 0 belonging to this. Right now it's a set, but eventually we're going, you need to verify this is a vector space. All right. So this L from V to W is the set containing all the linear maps from V to W, and that is a vector space. Or you check all the 6 properties defined for the vector space being satisfied for this definition. And when we're saying 0 is here, this is not a number 0. This is a linear map which maps every vector in V to the 0 vector in W. All right, so this is defined by 0V is equal to 0. All right, so to make it clear, this 0 is a function of, maybe we should see a map from V to W, and then this 0 here is this 0 is a 0 element in the vector space, the W. All right. And this book, sometimes I think if you look at the original definition, they did put like a pair of parentheses after that capital letter, but many times I don't know why, but for some reason the author just write that name of that linear map and then next to an element. All right. So if you want, you can actually put a pair of parentheses around the letter V there, if that help you to separate which is the map and which is the input. All right, that's not necessarily a bad idea. And then the other special linear map, or that we can check that is linear, that's pretty easy to check. The other thing we defined is the identity. All right, so we use the capital letter I for the identity. All right, and then this one, we define this as an element as a map from one vector space V into the same vector space V there. All right, because it's going to be strange if you have two different vector spaces. What do you mean identity? All right, that's not defined. So because this, look at the definition, it's pretty clear. It needs to be defined this way because it's defined by any V that I applied on V, you still get the same element. Okay, so it's not like a map that a V into something else in a different vector space. It's just from the V to the capital V to itself, and any small element V there, after you apply this map, you do not change it. So it's called identity, right? So nothing been changed. So then some other things relate to the polynomials. All right, and let's talk about the differentiation. All right, so we define a T. This is a linear map from the polynomial vector space to the polynomial vector space. Right? P, capital P of R, is the vector space containing all the polynomials. All right, no matter what order it is, all the polynomials defined over real numbers. All right, so this one is defined by T of P is the derivative of P. Right, for instance, if your input is a function x squared, after you apply this differentiation map, then you get 2x. All right, so that's how this thing works. And then when we have the differentiation, you probably guess there's also a counterpart. It's called integration. So we define the t are still from. Right now we talk about polynomials because the polynomials can be differentiated and integrated as many times as we want. All right, so nice functions. So that's why we talk about that. So this is, if you integrate this, is from 0 to 1, a p of x dx. All right, so we use a definite integral to define this function. Or this actually should from polynomial function to real numbers, because if the definite integral, when you evaluate that, you get a number, right? So then, of course, I mean, it's nothing significant for this 0 to 1, right? You probably could adjust that depending on your needs, right? But you can check, or you should check this definition also give you a linear map from all the polynomials to the set of all real numbers. All right, integration, and then multiplication. Right, by x squared. Right. So this one we define a t which takes a polynomial to a polynomial, and then this one the definition is the t of p of x, because they're trying to emphasize this is a polynomial function. This is equal to x squared p of x. All right. In other words, if you have something like input is x to the power of 10, right? When you apply this form over that polynomial, you multiply that polynomial by x squared, so you get x squared times x to the power of 10 is x to the power of 12. All right. So it's increase the order of that polynomial by 2. All right. That's what this does. Number 6, we have something. This is different, quite different from the earlier ones. Are we not using the functions? We call this a backward shift. So this one is defined from f infinity. I have to remind everyone, remember the fn is the vector containing n coordinates. The f infinity containing all those vectors is x1, x2, x3 up to, well, we do not terminate, we just keep going. So it's like a one, on one end is infinite dimension, right? It never stops. So it's infinite many numbers along the extended to the right hand side. So then this is defined by, if you have the input is x1, x2, or x3, and keep going, we never stop, and we just, the backward shift means you shift backward, so you're going to shift x2 to x1, x3 to x2, and so on. So we basically begin with x2, the next one is x3, and then we keep going. All right. So every number is being shifted to the left-hand side by one position. All right, so it's backward shifting. All right, and then let's look at one more. This one, all right, let's define the t, which is from R3 to R2. So this is a linear map. Take a vector in R3 to a vector in R2. Let's define this by txyz, because any vector in R3 can be represented by this. Is 2x minus y plus 3z, 7x plus 5y minus 6z. All right. So then, again, it's up to you to verify this is indeed a linear map. And this one, I think another suggestion is, well, think about what you have learned from your earlier like linear algebra class, right? So can you represent this linear map by a matrix times xyz? Right? Remember, the xyz is a vector in R3. If you end up with a vector in R2, if that can be represented by a matrix multiplication, then what the dimensions of the matrix will make that map well defined? That's the first thing I have to think about, right? If you pick up a matrix like a 4 by 5, it's probably not making any sense. And then after you determine the dimensions of the matrices, think about how those numbers like 2, -1, 3, 7, 5, -6, right? Where those numbers go. Right? So then probably you will be able to write this linear map into an equivalent matrix multiplication, and that's going to help you understand the things I think is in the section 3 of this chapter. All right, so keep that in mind. So generally, all right, so we can extend this idea a little bit. We can define a t from the Fn to Fm, or n and m could be the same, could be different, but we can take any vector in Fn, so there are n coordinates, and then turn this into a vector in Fm by this fashion. We have the a1, 1, x1, and then up to a1, n, xn. All right, so this may look like even more like what you have seen in a matrix multiplication from a linear algebra class. All right, the last one is am, 1, x1, all right, plus am, n, xn. All right, so think about this. All right, it's probably better to observe that specific definition above or help you understand the notation and the subscripts here, right? If you look at that xyz into our 2 case, your input, there are 3 numbers. So when you finish, you have 2 numbers, right? So in order to get the 3 numbers, generate each coordinate. So each coordinate must have something to do, in generally speaking, all these 3 numbers. So that's the same thing here, right? Each coordinate has something to do with all those n numbers, x1 up to xn, right? So that's why your sum, each sum are separated by those commas. Each sum is a sum of n terms. So that's, and if in front of each term, you need a coefficient. All right, and then that coefficient actually has 2 subscripts. Right, the first subscript tells you that's going to give you the first one on the right-hand side, or the second one on the right-hand side, and so on. And the second coordinate is going to tell you is match the x1, x2, or x up to xn. Right, and then how many of those coordinates we have on the right-hand side? Well, if you look at the case from the R3 to R2, there are 2 of them, right? So generally, if you map something from Fn to Fm, so there are going to be m coordinates here. So that's why the first one, every coefficient is associated with 1. In the second coordinate, every a begin with the first subscript begin with 2, and the last one, everything begin with the a sub m. And then those 1, 2, 3 up to n tells you it's the a sub m1 matched with x1, a sub m2 matched with x2, and so on. All right. So how many coefficients in total? All right, so think about this, right? How many actually a's altogether on the right-hand side if you have to make this well-defined? All right, so consider that question. So these are some definitions for the linear maps, let's talk about another, I don't know, it's a proposition or the theorem here is 3.5. Maybe let's call this a proposition. It's called the linear maps and the basis of domain. So what this proposition is trying to tell us is, well, if we remember in a finite dimensional vector space, everything can be spanned by a basis, right? So if you know what the span is, then basically you can use that to well characterize the whole vector space. So if we know a linear map is from V to W, if we understand how this map works on those spanning vectors, then that's enough to help us understand how this linear map works between these two entire vector spaces. So that's the spirit of this proposition 3.5. In terms of the statement, this one says, suppose we have the V1 up to Vn, or this is a basis of V, and the W1 up to Wm is in an another V there, another vector space generally speaking W there, right? Then it says there exists a unique linear map T, which is from the V to W, such that T of Vj is always equal to Wj, for j from 1 to n. So in other words, what this is saying is, well, if you have a basis and then you just pick up some other, this should be also the n here, right? And you pick up also the n vectors in W, right? And then you think, well, I want to create a linear map such that this linear map take the V1 to the W1, take the V2 to the W2, and so on. Right? Then we guarantee you, yes, there is always such a linear map you can construct. And actually, we're going to do this in a constructive way to show you what this linear map looks like. And secondly, well, there's only one such a linear map. There are no other ones going to take the V1 to W1, V2 to W2. If there is another one, that one is the same as the one you already defined. So this is we're saying there exists a unique thing. So this actually takes two steps. We're going to first show the existence, show well there is such a thing at least, and secondly show there is only one such linear map. So that's the idea of the proof here. So the way to construct this is, well, for any V belonging to this vector space, since this list is a basis, then we can always, for any V there, then this vector V can always be written as a linear combination of these basis vectors, or can be, in other words, can be represented by those spanning vectors here, right? So then we define the T of V as, well, probably this is the same as T of A1 V1 plus A2 V2 up to A sub n V sub n. So we define this as the A1 times W1, A2 times W2, and then AN times WN. Remember, this is your kind of like just on purpose make this definition, right? This is something, whatever definition you think it makes sense, and we think this makes sense, so we make this definition because originally we do not have any map here, right? We're just saying there are n vectors in the V, which is the basis, and then there are n vectors in W, and then you're saying is, well, now because the V vectors are basis, so any other vector or any vector in V can be represented as a linear combination. And then I'm going to take the same weights those scalars, and then I'm going to match them with the W at the same position. Or the V1 goes to W1, V2 goes to W2, and so on. And then I'm going to make the linear combination of the W using the same weights I got on the V vectors. And then this add together give you something W. And then this is like an artificial definition here, right? So then you're left to check two things. First, this thing you defined is actually, well, of course, that's a map, right? But you need to show this actually is a linear map. And then after that, you're going to show this is unique. If anything will satisfy your hypothesis in the proposition, that will just behave exactly the same thing, okay? So we need to show, all right, so first, we need to show this T is linear. So how do you show this T is linear? Well, check the two properties satisfied. So for any V1 and V2 in V, all right, so we have V1 can be written as something like maybe B1, well, oh, that's probably not a good idea. We already use V1, V2 in the basis, right? So for any we cannot use, let's use the U here, right? Probably U1 and the U2 are in V. So we can write the U1 as B1, V1, B2, V2, up to Bn, Vn. All right, we can write U2 also as a linear combination of this. Maybe you the C here. Okay. Then T of U1 plus U2 is T of those B1, V1, Bn, Vn, right? C1, V1, Cn, Vn. So that's just this can be represented by the linear combinations. However, we can group we can take out the common factors or from the sum of the sums, and then regroup them this way. And by our definition, right, so this is by the definition of T, right? How do you define the T? You said we're going to recombine them, replacing the V value with the W values. And then now let's rearrange this. Let's put this B1, W1, or B2, W2, and the B and Wn together, and let's put the C1 W1 up to Cn Wn together. But again, by our definition of T, this altogether is the T of V1, right? U1, use the U here. And then this is the T of U2, so it's plus. All right, so this way we proved what they call that additivity, right? So we have this. So now you can also check for any A in F, all right, and any V in the V here, all right, show the T of A times V is the same as A times T of V. There should be a small V here, all right? So let's left this as an exercise. Everyone can try this. If you understand what we talk for the sum, then for the scalar multiplication, it's not very hard to reproduce the same idea, right? To prove this, right? And if you can show this, then that tells us this T here, right, from the V to W defined by that fashion is actually a linear map, right? But we still have one more thing to show is we need to show this T is unique, right? So the uniqueness is not that hard to do, right? So I think I'm going to do this a little bit more formally than what the book basically kind of put a few sentences to explain that, are essentially the same idea. But what I'm going to do is let's assume there's another linear map T tilde which satisfy the same property in the hypothesis of your proposition, then we're trying to show the t tilde and the t eventually just going to be the same. All right, so let's assume, all right, t tilde is also a linear map from V to W such that it behaves the same way in the sense t tilde of any Vj is also equal to W sub j for any j from 1 to n. All right, then we left to show this t tilde for any v is equal to t for any v, right? Because what we mean the two maps equal to each other, that means they start from the same domain there, or the v there, end up with the same codomain w there, and then also for every vector, their output is the same. So that means these two are just the same as each other. All right. So obviously the way we define the t tilde is, well, we think this is a linear map from the way we, assumption on the t tilde is this is a linear map from V to W, so from the same vector space to the same vector space as T, and then we also want to satisfy the same property, or for all those basis vectors, it take each V sub j to W sub j, so what left to show is if they are the same or not. If it's the same, then this T is unique. All right. So how do we show this? Well, for any V in the V, right? So we can represent this V as V equal to something like A1 V1 plus A n Vn, right? By the definition of T, so the way we define the T is the T will take this V to A1 W1 up to An Wn. So that's our definition of T, right? And then now consider the other linear operator t tilde acting on the V. That is the t tilde acting on the A1 V1 up to A sub n V sub n. All right? But however, we know, by the linearity of t tilde, we know there's a linear map here. So we therefore, if it's linear, we have this. And then, but we also required this hypothesis is this going to take the V1 to W1, take the V2 to W2, and take the Vn to Wn. All right. So then these are all the A vectors match with the corresponding W vectors. So therefore, this tells us the map T and the t tilde, they equal to each other, and then this T is unique. All right, so this one is unique. So that is our proof. Of course, the book probably not formally set up another one shows them each other, but it says the same idea is by the linearity, then we can show they are equal to each other. All right, this is more like a formal proof here. All right, so this, I think, naturally probably concludes the first part of the recording, is regarding the definition of a linear map, regarding some examples, and one proposition. So in the second recording, we're going to focus on study that right now it's a set, capital L, parentheses V, comma W. All right, so we're going to look at that. All right, see you in the next recording.